Welcome to the next lecture. Here we are going to discuss about shear force and bending diagram. Let me move towards simply supported beam. Simply supported beam, you have this is supported, this is simply supported beam, wherein which you apply a UDL, uniform distributed load. The shear force and the bending moment behavior under UDL. The uniform distributed load UDL, a load spread evenly across the length of the beam, which is denoted as W, force per unit length, right. You always give it like force per unit, for example 10 Newton per meter, right. Suppose if there is a large area, very large area, and here you are trying to construct a building. So, now here what will happen at this portion, you will have a load distribution, right, load distribution, where in which we express it as a load per unit area. The shear force behavior, the shear force decreases linearly from maximum value at the support to 0 at the beam's midpoint, shear force. The bending moment will increase parabolically from 0 at the support to maximum to the midpoint. So, the simply supported beam for a length L carries a uniform distributed load of W across the entire length. Now, calculate reactions at support. The reaction at supports are, so the supports are, so I make it as A and B, right. These at the supports A and B are equal to the symmetrical load. The reaction force RA is equal to RB, which is nothing but W into L by 2, where RA and RB are vertical reaction forces at support A and B. So, support A and B are the extreme ends. So, you have here row this thing, and here you have a support. So, this is A and this is B. So, when we have to calculate the shear force A, B, when we are trying to calculate the shear force at left support A, where x equal to 0, VA equal to load, VA equal to reaction area, reaction at the point A, which is nothing but WL by 2. At any point x from A, the reaction force will be RA minus W into x, which is WL by 2 minus WX at the extreme right. So, we are taking a point, any point x, any point x in between. So, it is reaction force RA minus WX, which is WL by 2 minus WX. Okay. At the extreme end, it will be VB is equal to 0, as the shear force linearly reduces at the midpoints. Now, let us try to take the bending moment again for the same thing, bending moment A, B. Right. So, the bending moment at the support A and B is nothing but moment A, moment B, which is 0. So, at any point x from A, so it is RA, reaction force at RA into x minus W into x square by 2. This is a simple equation for parabola, and if you try to solve it, you try to get it a parabolic representation, right, something like this. Right. So, the maximum bending moment occurs at the midpoint where x equal to L by 2. This is L by 2. Okay. So, now let us try to solve a simple problem wherein which there is a beam which is supported at A, cantilever beam, and then the free end is B. Half of it, or maybe 1/4 of it has no load, and 2/3 of it has a uniform distributed load. and in the uniform distributed load you see here we have said 1 kilonewton per meter. The points are given as A is 2 meter from B and C is 1.5 meters from B. Now, let us try to draw the shear force and bending moment diagram. So, the UDL is 1 kilonewton per meter. The shear force diagram. So, between C and B, a distance of x from B, right. So, I am saying anything here, any distance, right. So, between C and B at any distance x from B, okay, the shear force is given as Fx equal to Wx, where Fx is equal to 1 into x. So, at point B, x is equal to 0, Fx will be equal to 0. At point C, x equal to 1.5. So, Fx at this point will be 1 into 1.5, which is 1.5 kilonewton. Right. So, from C to A it maintains the same, there is no strain. So, between A and C there is no load, right. So, now if you try to draw the shear force diagram for the same, it will be something like this. So, it started at a point 0. So, maybe you take a point C. So, this point. So, it will be something like this. It follows a straight line. So, you can take point C, point A, and here it is 0. So, here it will be 1.5 kilonewton and it also goes up to A 1.5 kilonewton. So, this is the shear force diagram for the given problem. Now, let us try to go and solve the bending moment of it. So, now the bending moment is diagram. So, first is bending moment at any cross section, any section between C and B at a distance x from the free side. So, that is going to be mx is equal to minus wx into x by 2, which is minus 1 into x square by 2. So, which is minus x square by 2. The bending moment will be negative as for the right portion of the section, the moment at x is clockwise. So, now at bending moment at B x is equal to 0, hence MB will be equal to minus 0 square by 2, which is 0. At C, x is equal to 1.5, hence MC will be minus 1.5 the whole square, which is minus 1.125 Newton meter. So, this I will make it as equation 1. From equation 1, it is clear the bending moment varies parabolic or it varies according to parabolic law between C and B. When we try to do a bending moment between A and C at a distance x from the free end, so the total load due to UDL is W into 1.5, which is 1.5 kilonewton. So this load of 1.5 is acting at a distance of 1.5 divided by 2, which is 0.75 from the free end, B, or at a distance which is x minus 0.75 from any section between A and C. Now, therefore, moment of the load at any section between A and C at a distance x from free end will be load due to UDL into x minus 0.75, which is mx is equal to minus 1.5x minus 1.5 into x minus 0.75. The negative sign is clockwise, right? So now from this is equation 2. From equation 2 to it is we get at C x is equal to 1.5 meters. So MC is equal to minus 1.5 into 1.5 minus 0.75, which is minus 1.125 Newton meter. At A, x equal to 2 meters, so MA is equal to minus 1.5 into 2 minus 0.75, which is minus 1.875 Newton meter, right? So if you see the bending moment, for C, it will be something like this. It will be till here, it will be a straight line, and then after this you will have a small curvature which goes up to here. So this will be point B, this will be point C, this will be point A. So from here to here it will be minus 1.875, and from here to here it will be minus 1.125, and here it will be a parabola. My drawing is not so great, so it will be a parabola. So here it will be linear, and then here it will be parabola, parabolic curve you can say. So this is how will be the shear force bending moment. If I want to put all the three in one go, so let me put the loading condition. They said, so this is B, this is C, this is A. shear force diagram SFD will be something like this. Okay, I have to go with respect to B. So, this is C, A, B, this is shear force diagram, right. And then if you want to do the bending moment diagram, so I have to extend it here. So, it will be from here to here something like this, linear, B, and then C, then I will have a, oh sorry, I will have a linear here, and then I will have a parabola here. I will have a parabola here. So, this is how will be the bending moment shear force diagram for a problem which is given in this form, a UDL loaded on a cantilever beam. Okay. Now, let us move to another interesting problem where there is a overhanging beam with UDL. So, you see here these are the two supports and you have a beam which is running, you can have a overhanging. For example, if you have a building and then you have a sunshade, there is a overhanging structure, right. So, similar to that, you will have a beam which is overhanging to the support and it is UDL. If the end portion of the beam is extended beyond the support, such a beam is known as overhanging beam. In case of overhanging beam, the bending moment is positive between the supports, whereas bending moment is negative for the overhang portion. Hence, at some point bending moment is 0 after changing its sign from positive to negative or vice versa. That point is known as point of inflection or point of contraflexure. We always call it as point of inflection. So, it will be something like this. So, you have a bending moment. So, from this point you have a support which is there. So, it falls down, the reaction force RA, reaction force RB, the length is 3 meter, 3 meter, 6 meter. If you are trying to do the shear force diagram, it will be something like this, and when you try to do the bending moment, exactly at this point you will try to see there is a change. So, this point E is called the point of inflection. So, this is A, point A, this is point D, this is point B. So, point B, point A, right, point A, point B, B is here, and then there is a inflection which happens between A and B, it happens, right. So, this is how it looks like. So, the point of inflection is the point where the bending moment is 0 after changing its sign from positive to negative. So, let us try to solve one simple problem in bending moment diagram. Draw a shear force and bending moment diagram for a overhanging beam carrying uniform distributed load of 2 kilonewton per meter over a length as shown in the point. So, here there are how many points are there? Point A, point B and point C. The overhanging is this portion between B and C is called as the overhanging. First, let us try to calculate. First, calculate the reaction force RA and RD. Okay. So, taking moments of all forces about A, we get RB into 4 equal to 2 into 6 into 3 plus 2 into 6, which is 36 plus 12. So, 2 kilonewton into 6 meter multiplied by 3 multiplied by 3, which is 3 plus 2 meter into 6. So, this you get an answer of 48, right, 48. So, RB is nothing but 48 divided by 4, which is 12 kilonewton. So, RA is the total load minus RB, which is 2 into 6 plus 2, right, 2 at the last, 2 into 6 is the total, right, minus 12, which is 2 kilonewton. So, now you have found out here RA and RB. So, now let us try to draw the SFD, shear force diagram. So, shear force at A will be equal to reaction force, which is plus 2 kilonewton. So, shear force between A and B at a distance x from A is given as Fx equal to Ra minus 2 into x, which is 2 minus 2x, right. So, at A where x equal to 0, it is Fa is 2 kilonewton. At B, x equal to 4, Fb equal to minus 6 kilonewton. So, the SF between A and B, will be a straight line or a straight line, and at A SF is positive and at B SF is negative. At A SF is positive and at B the SF is negative. Between A and B, so now between A and B SF is 0. So, this is equation 1. When you substitute Fx equal to 0, so in equation 1 you get 0. So, when you substitute in 1, 0 is equal to 2 minus 2x. So, where in which x is equal to 1 meter, where SF is 0. So, SF is 0 at a point D, hence distance of D from A is equal to 1 meter. So, now SF at any section between B and C at a distance x from A is given by Fx equal to Ra minus 2 into 4 plus Rb minus 2 x minus 4. So, when you solve it, you try to get 6 minus 2 x minus 4. So, at point B, x equal to 4. So, Fb is equal to 6 kilonewtons. At C, when x equal to 6, Fc is equal to, if you try to substitute it, you try to get it as 6 6 minus 2, 6 minus 4. You can go back to the drawing and you can see. So, that will be 6 minus 4, which is 2 kilonewton. So, if you want to write this also, so what I will do is I will explain that. So, this is nothing but 6 minus 2, 4 minus 4, which is nothing but 6 kilonewtons. That is how it comes, right. So, now if we wanted to draw the shear force diagram, the shear force diagram will be something like this. So, this will be point A, right. Then it will try to crisscross a point B, it will come to a point B, then it will go here, then from there it will go down and then you will try to see. So, point A, this will be point D. So, here it is 2 and then here which is D, which is 1 meter far away, you will have a D point, then you will get a which goes down, this is 6, and B which goes up is 6. So, this is negative, this is positive. So, you will get a shear force diagram for the UDL, whatever we have started with the problem. This is how you will try to get the shear force diagram. So, this is positive, then you will have a transition which comes towards negative, and at the point B it goes here. So, this will be C, and again here you will have a value of 2. So, and the inflection point is at D. Now, why is that important? Later when we try to solve the problem, we will try to see in bending moment how does it happen. When we try to solve the bending moment diagram, so bending moment at A is 0. So, first is between A and B, between A and B at a distance x, at a distance which is x, from A. Okay, so, that is nothing but moment of x is equal to R A into x minus 2 into x by 2, which is 2x minus x square. So, now the above equation, whatever equation is there, so this becomes 3. So, the above equation between A to B varies parabolically, right. So, now at point A, when x equal to 0, moment A will be 0. When at point B, when x equal to 4, moment B will be 2 into 4 minus 4 square, which will be minus 4 square, which is equal to minus 8 kilonewton meter, right. So, the maximum is at D. Maximum bending moment will be is at D, where SF is equal to 0. So, after changing sign, so at D, which is x equal to 1, so MD will be equal to 2 into 1 minus 1 square, which is 1 kilonewton meter. Now, bending moment, the BM at C is 0. So, the BM also varies between B and C according to by parabolic law. So, now the point of inflection. So, point of inflection will be between a point E, which is between A and B, where Bm is 0 after changing the sign, after sign change. So, the distance, so distance E from A is obtained by using mx equal to 0 in equation 3. So, what is equation 3? So, what we did mx equal to 2x minus x square equation. So, what do you get? You get 0 equal to 2x minus x square, which is x 2 minus x, where 2 minus x equal to 0. So, x is equal to 2 meters. Now, let us try to draw the bending moment keeping all the points. The bending moment for this diagram will be something like this. You will have a, then you will have a linear fall down, then you will have a taper. So, this is A, this is E, this is B, and this is C, right? And here you will have it as this distance is 2 meters and this will be 1, and here it will be 8, this will be 8, and here it is negative, here it is positive. Okay. So, we tried to solve 3 problems. So, all the 3 were pretty interesting. So, the first one what we solved was a very simple problem, where in which we had a cantilever beam where concentrated loads are applied at A, B, C, D. So, we drew this shear force diagram and bending moment diagram. Next, we went to UDL, which is applied to beam. So, here we try to solve it. So, UDL applied to a cantilever beam. So, here this is how the shear force diagram looks like, and this is how the bending moment looks like. So, you will have linear, then you will have parabola. This is in the bending moment. Then we saw a case of overhanging beam where UDL was applied. So, the shear force diagram looks like this and bending moment looks like this. It is always a good idea to draw all the 3 one below each other. For example, you will have a load diagram, then you will have a shear force diagram, then you will have a bending moment diagram. So, all the points over here, for example, point A, point B, point C, point D, which is there here, will try to superimpose with this. So, to recap what we covered in this lecture, we saw what is shear force, what is bending moment, what is the relationship between load intensity, shear force, bending moment, what are the sign conventions, why is the point 0 of shear important in bending moment analysis, the point of inflection. Given a cantilever beam with a point load at free end, calculate the shear force and bending moment. Then for a overhanging beam, then with a simply supported beam UDL. We saw 3 case studies. These are the references which we have used in preparing this lecture notes. Thank you so much.